Hello everyone, this is Katrina Mendoza, and once again, I am going to be your reporter for today. So for today's topic, since we had talked about the Gauss-Seidel method and we are still under the load flow analysis, our second method would be the Newton-Raphson. So our Newton-Raphson had been clearly understood way back in our third year college, wherein we had talked about it more of under the machines and in the industry, wherein we had dwell more on complex numbers in different iterations, focused in solving it manually as well as solving it through an Excel. But today we are going to tackle the Newton-Raphson more of under the load flow analysis. And way back in our last discussion is that in the Gauss-Seidel method, we had talked about the introduction of the load flow analysis, wherein it is really important for us to determine the different power, the current, the voltage, wherein it is under the load flow analysis as well. But there are two ways, or we have two methods wherein we are going to tackle and solve for our load flow analysis, which is our Gauss-Seidel, and today is the Newton-Raphson. So, okay. Here is again our roadmap to learning our Newton-Raphson method, wherein first, of course, we are going to talk about its definition. Second is that we are going to talk about its advantages again and its limitations, because as well, in our GS method or Gauss-Seidel method, we had talked about its advantages and limitations and had a little bit of comparison in advance of the Newton-Raphson method. So next is the flowchart, and this flowchart is used usually in digital computers, but still we are going to look at it and see the sequence so that we are able to compare it with the manual work that we are going to do. Next up is our derivation of formula. Of course, it is very important for us to know where our formula had been derived from, or the origin of our formula, so that we cannot forget about the concept from where or from the root the Newton-Raphson method had started from. So as for our example, of course, we are going to deal with today the 2 by 2 method, because of the fact that in the load flow analysis, in our next topic is that we are going to dwell more or further deeper in both the GS method and the NR method, or the Gauss-Seidel and the Newton-Raphson method. But today we are going to have a gist or an overview on how to solve the Newton-Raphson method. The same goes with our GS in our last discussion. And of course, lastly, that will be the end of our journey, and hopefully in the end, we are able to learn more about the Newton-Raphson in comparison in our third year, where we had just computed things manually as well as compared it with the Excel results. So now moving forward with our first discussion, which is the definition. It is essential for us to know what is the Newton-Raphson, pero in the last discussion is that we had clearly somehow compared the GS and the Newton. So today we are just going to have a recap, since some of the definitions of the Newton was been able to be given in our first discussion. So this is the start of us knowing the Newton-Raphson method. So our Newton-Raphson method is a powerful method of solving nonlinear algebraic equations. It works faster and is sure to converge in most cases as compared to the GS method. So it is indeed the practical method of load flow solution of large power networks. Now, if we are going to look back with our GS method or our Gauss-Seidel method, is that we can see the similarities, that it is also known to be as a method that is used in solving the nonlinear algebraic equations. But the thing is, the difference between them is that our GS method is used in smaller scales, in smaller ranges of buses, or in small power networks, wherein it is the reason why it is hard to converge into a more accurate or high accuracy of its values, wherein our Newton-Raphson is not very dependent when it comes to converging, as the number of the buses doesn't affect the accuracy or the number of iterations that the Newton-Raphson will result to. So that's the main difference between the two, wherein usually it is more practical to use the Newton-Raphson method, especially when you are dealing with large power networks. So furthermore, our Newton-Raphson is known to be as an iterative technique for solving a set of various nonlinear equations with an equal number of unknowns. Just to give an example, later we are going to deal with a two-bus circuit, and that two-bus circuit will yield to us knowing or solving for two unknowns. So meaning to say, if we have two buses, we are up or obliged to solve for two unknowns. As for three buses, we are obliged to solve for three unknowns. So that's hence the nonlinear equations with an equal number of unknowns. So next up, we have two methods of solutions for the load flow using our Newton-Raphson method. So the first one is that it can either be with the use of the rectangular coordinates for the variable, and the second method is the use of the polar coordinate form, wherein out of these two, we are not obliged, but it is more particularly and efficient to use our polar coordinate form, which is also used widely. So now we are going to talk about the advantages and the limitations of our Newton-Raphson method. As for the advantages, it is known to be as more efficient and practical for large power systems because technically, if we are to compare it to the GS method, our GS is normally used in smaller scales or small power systems that contains, of course, smaller number of buses. It possesses quadratic convergence characteristics, and therefore the convergence is very fast. Of course, in comparison with our GS, once again, its convergence na GS natin is slow because it depends upon or it is dependent to the number of buses that exist in that certain circuit or in our power system. Because the more iterations that it would converge to is that it will be literally fast in comparison to our Newton-Raphson because the number of iterations of our Newton-Raphson is independent of the size of our system. So, 2 to 3 iterations pa lang for both small and large systems is that the NR or the Newton-Raphson method can derive or can occur a high accuracy of its values by means of just 2 to 3 iterations. Wherein overall, there is a saving in the computation time since fewer number of iterations are only required. As for our limitations, is that this solution technique is difficult. Of course, we are now dwelling in a more complex solution to be able to come up with a lesser number of iterations and also to save computational time. So it is therefore to know it is therefore we are yielding more of a solution technique that is more complicated or difficult. It takes longer time as the elements of the Jacobian or Jacobian are to be computed for each iterations. The thing is that it is referred to as it takes more longer time because of the fact that we are adding a more complex technique, a more complicated one. We are adding more of the elements of the Jacobian wherein there is despite na meron na tayong y-bus admittance matrix, we are going to have eventually another matrix which is known as the Jacobian matrix. But nevertheless, with means of using this Jacobian matrix, the means of adding solutions, we are going to come up with a benefit that it reaches a high accuracy of obtaining the values by just means of their converging to 2 or 3 iterations. Next is that the computer memory requirement is large because due to the difficulty of its solution technique and also the longer time because of the additional elements of the Jacobian matrix, it will definitely require more of a larger memory in comparison to our GS because it is more simpler. It is considered to be a simpler technique. Now we are going to look at our flowchart for the Newton-Raphson method because this flowchart is drawn for the NR method using the polar coordinates and for load flow solutions. If I am not mistaken, usually this is used for programming in digital computers, but also, syempre, since it has the same process, this is somehow also the process that we are going to use later manually in solving for the first iteration of a two-bus system. So here we are going to start off our program with the start. Then way back in programming, we can visualize that this is also the construction in creating a block diagram in the sequence of our programs so that the iterations will just be looped and will create another form of iteration and will eventually lead us to the convergence of our answers. So here is the start, and further is that here is the read LF data and form the Y-bus. Our first step actually in manually solving for our Newton-Raphson is that we are going to form the Y-bus admittance as well, our Y-bus matrix. So next is that we have to assume initial bus voltages for our PI, wherein I is 2, 3, and so on and so forth. So this is also true when it comes to manually solving for it. We have to assume the initial values of our bus voltages, wherein later, since we are going to consider our bus 1 as a slack bus and our bus 2 as a load bus, we are to assume that they have um, the values of V magnitude equals 1 and our delta is equals to 0, or our angle is 0 degrees. So next is the self-iteration count R equals to 0. Then calculate for P for all buses except the slack bus. Calculate Q1 for all PQ buses. So here it is true that we are to solve for the other voltages of the buses first, and we are not going to solve for the slack bus or the V1 as it is the rule when it comes to the Newton-Raphson method. So next is to calculate the power mismatches, then to calculate our delta P and our delta Q, wherein here later you will see that we are going to use this formula, or we are also going to dwell more in solving for the delta P and delta Q as well. Then there are here different solutions that is further for the process of knowing the result for the Newton-Raphson method. The only thing is that it has a loop wherein, depending on the number of iterations that you wanted to come up with, you are always going to use the newer or the new value of the voltage that you had solved for. Like for example, in the first iteration, we are solving for our V2 and delta 2, and it has yielded to an answer of, like for example, 2.25 at an angle of 100 degrees. So that answer will be used in the next iteration. And further, the process will repeat by itself, or the process will just be repeated, and the new answer once again will be used in our third iteration, and so on and so forth. So that's only the idea of why there is a loop in this flowchart. Next up is that we are now going to dwell more deeper in the derivation of the formula. Actually, the derivation here is just simple because we are just going to derive for the answers or to the formula of our P and our Q, wherein next naman na process ng ating Newton-Raphson is to solve for our Jacobian matrix. Then going to be, we are now to set values for, or to solve values for P and Q, and our, then eventually we are going to solve for our unknown values. So we are, simply put, cut the story short, we are just to derive or see the derivation of the formula of our P and our Q. Okay. Here, our calculation of the net injected power, if we are to go back dun sa Gauss-Seidel method natin, we also derived the formula, right? And we had stopped with this formula flash in the screen. If we are to remember, ang Gauss-Seidel natin, sabi natin, to be able to come up with its formula, we have to equate a formula of a current into another formula of a current, where we had used the formula of the current from the apparent power. Diba? Ang apparent power natin is S is equivalent to VI conjugate. And our I conjugate was just derived to get the formula, which is PI minus JQI all over VI conjugate. For what reason? Our S is equivalent to PI equals JQI. Simply put, apparent power is equivalent to the difference of our real power and our reactive power. And that is going to be over our voltage I conjugate to simply get the formula of our current injected. Okay? So next stop is that itong naka-equate sa kanyang kabila. Saan ito nanggaling? It is also known to be as a formula of our current. Okay, so we had discussed on how we had arrived to this type of formula. We had used the Y-bus admittance matrix. So we had expanded it, we had simplified it, and in the end, we had reached to an answer of I equals Y sub I times V sub I plus our summation of N to K equals to 1 and K equals not equal to I, and Y sub IK times our V sub K. So after natin ma-equate yung dalawang formula is that tatanggalin lang natin yung denominator by means of multiplying both sides with VI conjugate. So this comes the answer. Therefore, ang ating formula now would be this one. Then after that, we are going to set values for y sub I, which is this, the magnitude, and also yung kanyang angle. As for VI conjugate, same goes. Dun sa YIK, VK, and TI, we are just to let values or set values or set formulas for them where each is which is going to be used in the later formulas. So as for the derivation of the Newton-Raphson formula, sabi nga natin we are to input those values na sinet natin doon sa formula, wherein after that we are just to expand it. After the expansion is that we are going to arrive with this simplification wherein we have to separate the real and the imaginary part of the latter formula wherein pi is equal to now this formula. So basically from expanding our formula, we are to simplify it so that we could have the values of pi and our qi. So our qi, naka-negative siya since nasa imaginary part or reactive power siya. But so that it could be um, derived to as a positive qi, we are to put the negative sign inside of our equation. So basically, if we are to simplify our formula, we are now going to use pi equals summation of n to k equals 1 and the magnitude of vi, vk, and vik and multiply it with the cos and the angle of ik minus our delta I plus our delta k. And same goes sa ating qi, wherein the only difference is that we, instead of cosine, is we are going to use the sine. So these two formulas are basically from our calculated net injected current in our network. So these two, which is the PI and QI, are going to be one of our main formulas to solve for the values of our two-bus sample later by means of using the Newton-Raphson method. So you have to remember that wherein later magpa-flash naman siya sa screen as our guide. Okay. So furthermore, after that is that of course we have to form our own matrix. And this matrix is just basically from this big one. So depende pa rin yun sa number ng ating buses, okay? Yung matrix natin, sabi natin noon pa sa Y-bus admittance, the number of buses is equal to the number of n in our matrix. So kung meron tayong 4 buses, there is going to be a 4 by 4 matrix. We have 2 buses, that's going to be a 2 by 2 matrix. Here, we are just going to simplify this whole big matrix into this short form wherein our delta P and our delta Q is equivalent to this Jacobian matrix, wherein later you are going to deeply understand the purpose of our Jacobian matrix and multiply it with our unknowns. Okay, later kasi ito yung magiging unknown natin. But still, depende siya sa example that we are going to solve for, okay? Pero here, since given as specified natin is this one and we are to form the Jacobian, so this is an overview of our example later. This is going to be our unknowns. Yung delta, change in our delta and change in our V. But basically, we are to solve for V2 and its angle. Okay? Now, to elaborate it further for us to understand it better is that we are now going to dwell in with our example problem. Our example problem today is just an easy one, for we are just going more of the introduction of the Newton-Raphson method, because in the load flow analysis, which is in our next topic, we are going to deal with much complicated for both GS method and TNR method. Okay, I'm using abbreviations, but just remember the GS is Gauss-Seidel and NR is our Newton-Raphson. Okay, this is the example problem. So we are to use the two-bus load flow for this example because it is easier to converge and look for our first iteration. So we have to take note that in this example, in this two-bus load flow, we are to let our first bus voltage be considered as a slack bus. So our slack bus, based on our last discussions, the GS method, we had introduced it to be as a voltage or a bus having a voltage of 1 at an angle of 0 degrees, wherein V1 would be 1 volt and our delta 1 is 0 degrees. As for our impedance here, sige, dun sa second bus muna tayo. In our second bus is that it is a known. Our V2 and delta 2 is a known and it is considered to be as our load bus. And this load bus is to be solved later. Our impedance naman, our Z12 or impedance natin, again, dun sa Y-bus admittance matrix natin, we all know that we are to form we are to form an impedance between two buses, and the impedance between these two buses would be 0.12 plus our J 0.16. And after that, we also have a value of our load here, which is 150 megawatts plus J50 and VAR or mega VAR. So basically, this is our real power and this is our reactive power. Okay, so now we are to solve for our V2 and our delta 2 using the Newton-Raphson, and we are to solve for the first iteration only. For what reason? Because it is time consuming. We are just to give an example today ng first iteration or one iteration so that in our next example, in the next episode or in our next discussion is that we are now it will be now easier for us to solve for more than one iteration or at least solve for a more complicated bus load flow like 3, 4, or 5. But basically, we are to dwell first with the introduction on how to solve for our Newton-Raphson in the first iteration in the two bus load flow. Okay, we have two unknowns, which is V2 and delta 2. And now we are needing two functions. And that two functions later would be our P and Q. Here, as you can see, the order of the function, delta is going to be solved first before our voltage. So let X be our delta 2. Since yun ang una natin isosolve, then our V2, which is our voltage 2. So our function, sabi nga natin, we have two unknowns. Therefore, we have two functions, and that's going to be our P2 and our Q2. So we have to take note of these two functions, as these two functions will be our source of expansion later. This is going to be the main formula wherein we are to expand it in input variables or input values, and therefore we are going to solve for our P specified, Q specified, and eventually our S2 or our delta 2 and our V2. Okay, so nilagay ko lang ulit dito yung ating circuit so that meron tayong babalikan or as a reference natin. Now, flash in the screen is our step 1. The step 1 in solving by means of using the NR method is to form our Y-bus matrix. Kung mapapansin ninyo is that we had started our discussion with the Y-bus admittance matrix, then with the cron. But the cron went back to our Y-bus admittance or use our Y-bus admittance matrix. Then the cron from the LU, we still went back in creating matrices. So here, our step 1 once again, we went back to our Y-bus admittance matrix knowing our Z12 may given tayong Z12 which is 0.12 plus J 0.16. So we all know that in solving for our admittance, it is just mainly or basically the reciprocal of our impedance. So that's going to be 1 over Z12. Now, here is our Y11. Hindi ko lang siya nalagay, but this is our Y11, Y12, Y21, and our Y22. And our principle or our law when it comes to diagonal, kung matatandaan ninyo, our diagonal and off diagonal. Diagonal, this basically is the sum ng lahat ng reciprocal ng impedance natin to get our Y11. Diba? Lahat ng may connection sa ating first bus. Here, isa lang naman yung impedance na given natin. Diba? Ang given lang natin is Z12. So basically, that's 1 over 0.12 plus J 0.16. which is our y11 over here. Wala namang iba tayong impedance na given or admittance na given dun sa circuit natin or dun sa load flow natin. So, that's going to be our y11. And our y12, sabi natin, if off diagonal siya, is we have to multiply it always with negative 1. So our negative 1 multiplied by our z12, the reciprocal of z12, is basically negative 1 over 0.12 plus j 0.16, as you can see over here. Same goes sa ating y21. Since y12 and y21 is just basically the same, that's going to have, this is going to have the same answer as y12. And as for our y22, lahat ng nakakonect sa sa bus 2 natin, and that's going to be positive. And given lang naman natin is z12. So basically, the reciprocal of 0.12 plus j 0.16. And to simplify it further, if we are going to solve it, is we are going to arrive at an answer of 3 minus j4, negative 3 plus j4 for y12. For y21 is negative 3 plus j4, and for our y22 is 3 minus j4. Pero sabi natin, it is more convenient or it is more efficient to use and more understandable to use our polar coordinates or in the polar form. And now, we are to change it to our polar form. So basically, yung ating y11 natin is to be changed into polar form, which is 5 at an angle of negative 53.1301 degrees. And as for our y12 is 5 at an angle of 126.8699 degrees because naka-negative siya. So basically, ang makuha nating angle will be positive in this instance. So same lang to ng ating y21 and ng ating y22 is 5 at an angle of negative 53.1301 degrees. So it is just so basic to solve for the two-bus load flow and to understand it in comparison to 3, 4, or 5 or nth number of buses in comparison to this. Now here, we just have to take note na yung value natin ng ng delta 2 rather, and our V2 would be 0 and 1. Parang nagle-let lang tayo. Let X be delta 2 be 0 and our V2 be 1 because later, kailangan natin ng old values ng delta 2 and V2 to come up with the new value of our delta 2 and our V2. So, you will understand it further later. But as for now, this is our step 1, to solve or form our Y-bus admittance matrix and to change it in polar form. Okay, now flashing the screen would be the reference of our Y-bus. And then yung Y-bus na na-form natin kanina, na change lang natin sa polar form. Okay, so now we are going to use it in our step 2 to calculate our P2 and our Q2. Our P2 is basically this formula, and this formula had been derived din, sabi ko sa inyo kanina, na we have to take note na formula ng ating P2, yung may summation sign. So basically, in-expand lang natin siya, and we have to look for or insert the values of V1 times V2. Lahat ito naka-magnitude, yung magnitude lang kukunin natin, times Y21, then cosine our delta 21 plus delta 1 minus delta 2 plus our V2. Then i-square natin yon, then our y22, then cosine delta 22. So our v1 is 1 since it is the slack bus. V2 natin is 1 also since yun yung nakalet natin kanina. Y21, as in yung y21 natin dito sa bus, this is going to be y11, y21. And since magnitude lang, that's going to be 5. So 5. Then cosine, so angle natin for this one is 126.8699 degrees. Then ang S1 and S2 natin, since slack bus ito, 0. Since this let natin is 0, 0 siya. V2 natin is 1, so i-square times ang magnitude ng y22, which is this one, so that's going to be 5. Then cosine ng ating angle ng y22, which is negative 53.1301, which is going to be inputted in the area over here. So if we are to solve ng this equation, ang makuha natin dito is negative 3.00 something. This here, positive 3 point something. So, negative 3 plus 3 is just basically, we will end up with an answer of P2 is equivalent to 0. So, next we are to solve for our Q2. Ang Q2 natin is naka-negative lang siya and naka-sign siya, but same goes dun sa formula ng P2. And also na-derive siya from expanding yung ating may summation kanina na naka-summation kanina, wherein I have said na we have to take note. So basically, yung ating V1 natin is 1, our V2 is 1 as well, Y21. Y21 is this one. So 5 sine and angle ng Y21 is 126.869 degrees. Our delta 1 and 2 is 0. Ang V2 natin is 1. I-square natin yon. Y22 is over here. This Y22 and this is going to be 5, then sine, then yung angle niya, negative 53.1301, and do the math, we will still arrive with a value of 0 for our Q2 calculated. Okay, now, naka-flash again dito sa screen yung ating reference circuit natin or reference 2-bus load flow. So, this reference will be needed for us to solve for our step 3. Ang step 3 natin is to calculate for the specified values of our P2 and Q2. Take note na kanina, balikan lang natin, we had calculated for P2 calculated and Q2 calculated, which is both 0, which is necessary because kailangan natin siya for this formula. Okay, so P2 specified natin, parang nag-proving lang tayo dun sa kanina, wherein we just solve for the variables or the values that we need to input in this step 3, which is now to solve for our specified values of P2 and Q2 as well as the change in P2 and change in Q2 na kailangan natin to input doon sa matrix later. Okay? So, that's going to be important. Ang P2 specified natin has a formula of PG2 minus P sub P2, wherein since ang ating second bus natin is going to be as a load bus, so ang PG2 natin is going to be as 0. So, minus siya sa ating PD2, which is yung nasa load natin, this one. Yung power natin, real power natin is 150 megawatts. So, we have to divide it by 100 to arrive at an answer of 0 minus 1.5 equals negative 1.5 per unit. So, as for the change in P2 is P2 specified minus P2 calculated. P2 specified natin is negative 1.5 per unit minus yung ating kaninang P2 calculated, which is 0. Baliktad pala to. Baliktad yung lagay ko. Pero that's basically it. 0 minus 1.5. Either way, we will still come up with an answer of negative 1.5 per unit. Same goes sa pag-solve natin for Q2 specified. Q2 specified is going to be QG2 minus QD2. So that's 0 minus anong reactive power natin sa load? That's J50 MVAR or MVAR. So that's 50 divided by 100 to come up with a decimal answer of negative 0.5 per unit. So for the change in Q2, that's going to be Q2 calculated minus Q2 specified. So that's 0 minus 0.5, resulting to an answer of still negative 0.5 per unit. So we have to again take note of the answers of the change in P2 and change in Q2 because that's going to be P negative 1.5 and Q is negative 0.5. It is going to be useful later for us to remember it now para we better understand kung ano yung nilalagay natin sa matrix. Okay. Now, for our step 4 is to find the elements of the Jacobian matrix or the Jacobian matrix. And that Jacobian matrix would be this part. Ito yung part na yun. Kung natatandaan ninyo na ito yung formula natin kanina doon sa last part ng derivation, right? The difference is only nandito yung ating P2, naka-equal naman siya. So dito yung P2, Q2 natin, then this is the Jacobian matrix or Jacobian matrix, then this is our delta 2 and V2. So that's basically it. Parang pinapakita lang dito on how to form our Jacobian matrix or Jacobian matrix. Wherein here, we are to solve for the elements of the Jacobian matrix wherein those elements can be solved by means of doing these formulas, itong apat na ito, wherein basically we are to differentiate, specifically partial differentiation. So partial differentiation of P2 all over delta 2, partial differentiation of P2 over V2, partial differentiation itong Q2 over delta 2, and Q2 over delta, that's V2, sorry, V2 to, V2. Now the question is, what are the functions or what are the formulas to be used in the next step? So here, sabi natin, we have to do partial differentiation wherein we are not going to step by step sa partial differentiation. Na? We are now basically knowing the concept that from this equation, Q2 and P2 is that we have to differentiate it, do partial differentiation. And for our first, let's say, at a J11, this is J12, J21, and J22. Now we are to solve for J11 by means of partial differentiation. We are to arrive with this formula. Okay, so our formula is for magnitude V1 times magnitude V2 times magnitude Y21 and our sine, then the angle in 21 plus our delta 1 minus delta 2 plus our V2 squared Y22 cosine the angle in y22. So, if we are to input our values is going to be V1 ay 1, V2 natin is 1 din, kaya naka-squared na to. Our y21 is 5. Our sine, angle ng 21 natin. Nandun na yun sa ano natin kanina, right? Nasa y bus admittance. So, basically, ang 2-1 natin is 126.8699 plus 0 and yung ating delta 2 is 0 as well. And this is going to be cancelled as the value for this is 0. Now, after inputting our values, we are now to solve, do the math, and we are going to arrive with an answer of 4. And that 4 is going to be our J11. So, input natin siya over here. Ito yung 4 natin. Okay, since may value na tayo ng J11, we are to solve for J12 right now. So, that's going to be P2 all over V2. So, by means of differentiating once again, makukuha natin itong formula na to. And this formula, kailangan natin i-substitute yung values. V1 is 1, Y21 is 5, cos natin, then this is going to be, yung angle is 126.8699. This 2, let 0 na siya. Then 2 times V1 is 1, by 2 is 5, and cosine natin is negative 53.1301 yung angle natin for sub 22. So, doing the math once again, we are to arrive to an answer of 3. So, this is ating J12 is going to be 3. So, this is 4, 3. So, remember lang natin yan para mamaya makita nyo na it is just inputted in our Jacobian matrix. Now, to solve for our J21. Our J21 now is Q2 all over delta 2. So, from that, we are to arrive with this equation. And may negative sign na siya, as you can see dito, sabi natin kanina, if we are to expand this, we are going to have, actually may negative to, hindi lang siya nalagay. So, yan. So, now to solve for our Q2, substitute the values for V2 and V1, which is equal to both 1. And yung ating Y21 is 5, cosine 126, 8699, and our delta 1 and 2 is basically 0. So to solve for this, we are to arrive to an answer of negative 3. So we have to input it over here, negative 3. Next, our last, which is J22, and J22 is Q2 all over delta 2. Again, by means of differentiating, we are to arrive with this formula and substitute our values, which is V1 is 1, our Y21 is 5, sine 126.8699. So, our delta 1 and 2 is basically 0. Then, minus natin. Since may 2 tayo, that's going 2 times 1 times 5. This is 1 and 5. And sine yung angle natin ng sub 22, which is negative 53.1301. So, lahat to, ng values na to, kung nalimutan ninyo, is we can look it up in our given values, which is V1, and yung S1 natin is 1 at an angle of 0 degrees. Same goes sa values natin ng V2 and our delta 2, which is 1 angle of 0 degrees. And yung lahat na natitira, which is yung may angle sub 22, and yung Y21, and so on and so forth, pwede natin makita sa ating Y-bus admittance matrix. So by doing the math, let's just go back. Ang answer na natin is negative 4. So here, our J22 is equal to negative 4. Now, by means of inputting it in our matrix, or our step 5 right now is to solve for the inverse of the matrix. So first is, if you can remember, ito nga yung ating matrix kanina na pinakita after the derivation of our formula for the Newton-Raphson. So basically, this is the Jacobian matrix. Now, we have to input our values in the Jacobian matrix. So this is J11, sabi natin kanina, this is 3, this is 4 rather. So this is 4. Tapos our J12 is going to be 3. Tapos negative 3 naman to. Negative 4 naman ang J22. So, basically, in-input lang natin siya dito. Then, sabi ko sa inyo kanina, we have to remember the values of the change in P2 and change in Q2. So, that's going to be negative 1.5 and negative 0.5. So, you can just always go back to see kung saan nanggaling yung P2 and Q2 natin. Pero we had arrived at an answer of negative 1.5 and negative 0.5. We are just here basically substituting the values of the variables depending on sa lahat ng na-solve natin kanina. So now, since may values na tayo dyan, we have to inverse the matrix of our Jacobian. So Jacobian natin is 4, 3, negative 3, negative 4. This 2 by 2 will be inverse by means of multiplying or raising it to negative 1 kasi it's just the same. That's going to be 1 over the matrix. So from solving this, we are to arrive at a new set of answers in our 2 by 2 matrix, which is 0.16 and negative 0.12, 0.12, and 0.16. After that, we are just to rearrange this. Since ang hinahanap naman natin is delta 2 and V2, hindi itong P2 and Q2, we just have to rearrange this set of matrices. So, ang ating delta 2 and V2 will be equivalent to the Jacobian matrix times the change in P2 and Q2 natin. Since we had created and rearranged our matrix, is that we are now to create an equation. So, our delta 2, para makuha natin yung delta 2, is that we have to multiply 0.16 sa ating negative 1.5 and add it to the product of negative 0.12 and negative 0.5. So, from that, makukuha na natin yung ating value ng partial value, if I say so myself, ng ating delta 2. Kasi may gagawin pa tayo dun sa na-compute natin yan. Later, may kita ninyo. And our V2, to get that, is that we have to multiply negative 1.5 to our 0.12 and add it to the product of 0.16 and negative 0.5. And if we are to put that in an equation, makukuha natin a change in S2 natin is 0.16 times negative 1.5 plus negative 0.12 times negative 0.5. Do the math, we are to have an answer of negative 0.18 radians. So, if we are to multiply this to negative 0.24 siya plus multiply this to positive 0.06 siya. So, if we are to get the answer, that's still going to be negative 0.18 radians. As for our V2, sabi natin multiply 0.12 and negative 1.5, then add it to the product of 0.16 times our negative 0.5. So, this 2, ang product nito is negative 0.18. This 2, ang product nito is negative 0.08. And if we are to add this to it, that's going to be negative 0.26. So, we have the answer. But is that the final answer? No. The thing is, kailangan natin makuha yung ating new value ng delta 2 at new value ng ating V2. So, how? The first thing is that kung natatandaan ninyo, nag-set tayo ng values for our delta 2 and V2, which is 0 and 1 respectively. Okay, now to input it in our equation or our formula, our delta 2, our new delta 2, is equivalent to our old delta 2, which is 0, plus our new change in delta 2, which is negative 0.8 radians, as you can see over here. So that's 0 plus negative 0.18, we will arrive to an answer of negative 0.18. But it is in radians. So we have to convert it into degrees since kailangan natin siya makuha in V at an angle of. Okay? So to be able to change our radians to degrees, that's simply multiplying 180 all over pi, and we are going to arrive at an answer of negative 10.3132 degrees. So now we have officially the value of our delta 2. We are to solve now for our V2. Kung natatandaan natin, it is part of our rule to solve for the degrees or the delta first before our voltage. So our new value of our V2, that's going to be the old V2 plus our delta V2. So, ang old natin, base dito, is 1. So, that's going to be 1 plus, and yung ating delta V2 is negative 0.26 daw. So, or based sa calculation natin. So, that's 1 plus negative 0.26. We are to arrive at an answer Press your calculators, that's 0.74 per unit. Now, to construct for our final answer, our final value for the two-bus load flow is that we have 0.74 at an angle of negative 10.3132 degrees voltage. Okay, so here mapapansin ninyo that our delta or our angle is in negative. So delta 2 is in negative because this is the receiving. So yung slack bus natin will send power to this. Therefore, it must be less than 0. So that is why it is negative. So therefore, our values of V1 and V2 will be 1 at an angle of 0 degrees voltage for V1 and our V2 is 0.74 at an angle of negative 10.3132 degrees voltage. So these values, yung extracted value natin or our V2, which is the value for our first iteration, we will use this to solve for our next iteration. And the same process will be undergone for the next iterations. I have explained it further kanina. So basically use V2 for the next iteration and yung makukuha mong value, new value for the second iteration is that will be used for our third iteration. So that would be the end of our journey and hoping that you had observed well, learned well, and listened well to our discussion for today because this is going to be an important foundation for our next topic, which is the load flow analysis itself. And we are going to dwell more on difficult examples and explanations regarding that. Kasi the more na dumami yung ating bus, the more nadadami yung ating calculation since there are more unknown values to be solved for. So we just have to take note and remember that the Newton-Raphson method is practically used or is known to be as a practical method to solve for the unknown values in a certain non-linear algebraic solution or non-algebraic problems wherein it is used for large power systems in comparison sa GS method natin, which is just limited to our small range of buses or the small power networks. So again, this is Katrina or Mendoza, and thank you so much for listening. If you have any questions, you can find me at Katrina at comendoza@slc.edu.ph. Again, I'm reminding you to stay positive and always look at the bright side. Again, this is your reporter, and see you in the next episode. Bye, guys.